Here we'll be looking at integer exponents in scientific notation. Feel free to pause any time to read the text on any of the slides. Here we're looking at the product rule for exponents, which basically says if we have an a to the m times a to the n, then we add those exponents together. You can see some examples with the work already done really on them here. So looking at this first example, 3 to the 4th times 3 to the 7th, we just add the 4 and 7 together. That's how we get 3 to the 11th. A little tricky one here. We have just the 5 here, so that's really a 5 to the 1st power. So we add the 3 and 1 together and get 4. Here, even if we have 3 y's, really we just add those 3 exponents together, 3, 8, and 2, we get y to the 13th. With this example here, the y's, we could just think of those separately, so we add the 2 and 4 together, and we just multiply the 5 by the negative 3, that's where we get the negative 15 from, and then the 2 and 4 makes the 6. Similar type of example here with e, looking at what we have, just kind of rearranging things so that like terms are adjacent. So the 7 times 2, p to the 3rd times p to the 5th, and q to the 1st times q. So we get 14 from multiplying the 7 and 2 together, 8 from adding the 3 and 5, and 3 from adding the 1 and 2. And then here, x squared times y to the 4th, the product rule does not apply since the bases are different. Looking at 0 and negative exponents, we'll start with 0. So if a is any non-zero real number, then a to the 0 is 1. 0 to the 0 power is undefined. Again, there's nothing for that. Here just looking at some different examples and really focusing on what is the base for these different problems. So here 6 to the 0 power is 1. And then over here, if we have a negative 6 to the 0 power, the entire base is negative 6. So that entire base, negative 6 to the 0 power, is just a plain 1. Now compare that to the problem here, where the base is really just 6. So the 6 to the 0 is 1, but we still have that negative, so we end up with negative 1 as the result. Even throw in an additional 0. Again, the parentheses are important there. We take care of the negative 6 to the 0 power first, which just gives us 1, but then we still have that 1 negative there. Make sure you don't try to cancel those 2 negatives out. Again, that would be doing a multiplication step before an exponent step, which would be a problem. Looking at this one, 5 to the 0 plus 12 to the 0, those are really both 1, so the result is just 2. And then 8k to the 0 power. The key here, the entire base 8k is being taken to the 0 power. So it's really just 1. Again, notice the condition there that works so long as k does not equal 0. So important there to consider the possibility of a variable being equal to 0 as well. And here's our basic rule for negative exponents. So if we have an a to the negative n, then that's the same as having a 1 over a to the n. That makes the exponent positive. So really taking it and moving it down changes the sign on that exponent. So we see some examples here. This one's already worked out. The 2 to the negative 3rd is the same as 1 over 2 to the 3rd. If we look at b here, that would just end up being 1 over 6. We don't need to put the 1 as an exponent. It's fine to leave that off. If we look at c, the entire 5z would move down to the denominator, so 1 over 5z, and I need parentheses around that still, so I can show that that is now to the positive 3rd power. Comparing that to d, where only the z is being taken to the negative 3rd, so then the 5 stays on top, and the z to the 3rd would move down. Here with the negative in front of the m, we will have a fraction, so it does not necessarily matter where that negative goes, but the base is really just the m. But just like any fraction, the negative could go on the 1, it can be out in front, or it can be on the m. Now here, the negative being inside the parentheses makes a difference. It's still 1 over a negative m squared. Of course, now we can see, well, that would just be an m squared because the negative is part of that squaring, so that would cancel out. If you wanted to evaluate this one, it would be 125z cubed in the denominator there. Looking at these, 3 to the negative 1 would be 1/3, 4 to the negative 1 is 1/4, 1/3 is the same as 4/12, 1/4 is the same as 3/12, so we get a total of 7/12. Very similar here, we get 1/5 minus 1/2. 1/5 is 2/10. Oops. 1/2 is 5/10. So we get a negative 3/10 for that one. Here are some special rules. So really important shortcuts mostly for dealing with negative exponents. So if you have a negative exponent in the denominator, it really just moves up to the numerator and becomes positive. If you have a fraction where both top and bottom have negative exponents, they just, again, move down or up in order to make that exponent positive. So you can see a worked out example here. Again, the nice thing about the shortcuts is you don't have to go through really all of this stuff. You just jump from the beginning all the way over to the 2/3 power, which of course ends up being 8. Same thing here with that fraction. We just use our shortcut here when we get to skip all of this stuff. We just go from here all the way over to here. So the 3 comes up, 2 goes down, 3 squared is 9, 2 cubed is 8, so we get 9 over 8. So shortcuts are very handy. You get to skip over all of this stuff. Quotient rule for exponents really says that when we have that quotient, we subtract the denominator from the numerator as that exponent. And again, we can even flip that around if we want to, but we'll just kind of go with that for now. Looking at our first example here, we just take this 2 away from the 7, so we get 3 to the 5th power. At this point, I'm just going to leave that as 3 to the 5th power. As our second example, we just get 6 minus 2 for the exponent, so we get p to the 4th power. Our third one, we have our k's here, so we would just do 7 minus 12. So we do get k to the negative 5th. We never want to leave that with a negative exponent, so we go k to the 5th. One thing I look at there is, since the 12 is bigger than the 7, I just think of the difference between the two. Doesn't matter which way we work that, but generally think of that as 12 minus 7, which gives me 5. And then since the 12 is bigger than the 7, I know that the k will end up in the denominator. So one thing I do is kind of just avoid that process of subtracting the 12 from the 7 and getting a negative and then flipping it down. I just try to look at this and say, okay, where is the k going to end up? Well, there's more k's in the bottom, so it will be in the bottom. That's where we'll have a positive exponent. Well, how many more does it have? Well, it has 5 more, so I know it will be k to the 5th power. So I do try to think of it that way. Here with the 2's, there's more 2's on top, and really, if I'm going to subtract, I would be subtracting a negative 3, so I really end up adding, and I get 2 to the 10th power. And again, for now, I'm just going to leave that as 2 to the 10th power. Then I've got example E here. So there are more 8's on the bottom. So again, one thing I can do is just look at, well, what's the difference between 5 and negative 2? Well, that's 7, and so we'll end up on the bottom. If you just do the typical process, you go negative 2 minus 5, which of course will be 8 to the negative 7th, which would be 1 over 8 to the 7th. And again, of course, you could evaluate that. For now, I'm just going to leave that as it is. Now with G, we have the Z's. They both have negative exponents, so I could just use our property here, but we just went over the negative exponent property, so why not flip that? Z to the 8th over Z to the 5th. And then I can see I'm just doing 8 minus 5 and getting z to the third power. G, oh, I guess I missed f over here. So f, again, really this is a 1 for the exponent, but I would end up subtracting the negative 1, so I end up adding it. So, and of course 6 squared is just 36. Power rules for exponents, so we have a few of them. So power of a power, we multiply those exponents together. Power of a product shows that exponents distribute over multiplication, so that exponent applies to each part of that product. And then power of a quotient, again, really the same as power of a product. The exponent distributes to both parts of that quotient, so we get those there. Notice the stipulation there, that works so long as b doesn't equal 0, because if it does, then it's undefined. Looking at our examples here, in our first one we just have a power, so we multiply the 8 by the 3. Of course we get 24. In our second one, this is a power of a quotient, so we distribute that 4 to both the top and the bottom, and we get 2 to the 4th over 3 to the 4th. 2 to the 4th being 16, 3 to the 4th being 81. It's not too tough to do that. In C we have another, or we actually have a power of a product. So again, what happens here is our exponent distributes. So we have a 3 to the 4th and a y to the 4th. Like we just saw, 3 to the 4th is 81. Here we've got a combination of power of a product and power of a power. So the 6 would get squared. The p to the 7th also gets squared. Of course, 6 squared is 36th. And if we square p to the 7th, we multiply those together, we get p to the 14th. Here we've got really all three rules together. So we would take the entire numerator, negative 2m to the 5th, would be to the third power, and the denominator would also be to the third power. In the numerator we have the power of a power and power of a product. So you have the negative 2 would be to the third power, and m to the 5th would also be to the third power. The z is done already, really. And if I cube negative 2, I get negative 8, and multiply the 5 by 3, since that's a power of a power, I get m to the 15th, and then z to the third. Again, a couple other special rules for negative exponents. Again, negative exponent, a to the negative n is 1 over a to the nth power. If you have a negative exponent of a fraction, then you just flip the fraction over. It's the reciprocal to the positive exponent. So something like a here, we just flip the 7 over 3 over. That's getting squared, so we square both the top and bottom. We get 49 over, so that's a 9. And then very similar with the 4/5, we flip that over, we get 5/4 to the third power. 5 to the third is 125. 4 to the third is 64. Here's just the rules for each of those, so again, feel free to pause and take a look at that as much as you want. Here we just want to simplify so that we don't have any negative exponents in the final result. Let's see, so looking at this first one, we can add the 2 and negative 5 together. We get 3 to the negative 3, which then would be 1 over 3 to the third power, which would be 1 over 27. Next one, we can add the x's, the exponents together, negative 3, negative 4, and 2. So it would be negative 7 plus 2, so it would be negative 5. Of course, we don't leave any negative exponent there, so 1 over x to the 5th. For c, this is a power of a power here. So we really just multiply those exponents together. So negative 2 times negative 5 would be just a positive 10. I'm just going to leave that for now, not too worried about what 4 to the 10th power equals. And then I'm going to jump up to e here. So multiplying the negative 4 by negative 6, we get negative 24 which then becomes 1 over x to the 24th power. F, now we're getting a couple different things here. There's a few different ways you can do this. I think I'm just going to kind of distribute the negative 2 and do the power of a power property at the same time. So it would be 2 to the negative 6th power, x to the 4th power, ends up being x to the 4th over 2 to the 6th. And 2 to the 6th is 64. So x to the 4th over 64. And then with G, we get, I guess I'm not sure why I did F before E, so maybe I'll come back over here and do E here. One thing I could do is just move the x's and the y's with the negative exponents up and down, so the y to the 5th would come up, y to the 2nd stays where it is, x to the 4th goes down, x to the 2nd stays where that is. Now with those positive exponents, I just add those together. 5 and 2 make 7, 4 and 2 makes 6. First thing I would probably do with G would be, well, if I do a little bit with the left here, I can distribute that 2 to each piece, so that would be a 9. And I'm really multiplying these 2's together to get 4, and then squaring the y at the bottom. With G, there's a couple things I kind of feel like doing right away, but I think I'll just kind of leave the parentheses, do the 4x cubed, and then the y squared will come up because it was a negative exponent in the bottom. Now the funny thing is, since it's all to the negative 1 power as well, it's all going to end up in the denominator. So we get a 4x cubed y squared in the denominator. Now the 9 and the 4 won't reduce at all, so I get a 9 on top and a 4 on the bottom. I do have an x to the 4th here and x to the 3rd there, so that's a difference of 1. So I get just a plain x on top. I've got a couple of y's on the bottom, a y and a y squared, so I add the 1 and 2 together, and I get a y cubed. So 9x over 4y cubed on that one. Here just a bit about scientific notation, so you can feel free to pause and read that. So writing each number in scientific notation, again, I've got a little bit different process to do. What I look at is, I know it's going to be 8.2 times 10 to a power. What I look at is that it is a 6-digit number. I can see pretty quickly that it is a 6-digit number, so I know that my exponent then on a 6-digit number is 5. On this second one, it's a small number, so I know it'll be 7.2 times 10 to the negative power. And I know the power will be the same as the number of zeros that we have there. So rather than kind of doing the jumps, I just look at how many zeros that is. Well, that's 6 zeros, so I get the negative 6th power there. And then the last one, 4.62 times 10 to the negative power, negative 4.62. And again, I just look at the fact that there's 5 zeros there, so it's the negative 5th power. So here we're looking at converting to standard notation. So if we have 6.93 times 10 to the 7th, again, when I look at it, I do it a little bit differently, but I look at the fact that that's going to end up being an 8-digit number. So I've got 693, that takes up 3 of my digits. So I know that I have 5 zeros. Again, it's a little bit different way of looking at it, but to me that makes it much simpler. For a number with a negative exponent, the negative exponent really just tells me how many zeros I have before my number, but that is including a proper 0 before the decimal point. So I just do 6 zeros, and then I have my 4, 7. Now the negative 1.083 times 10 to the 0 power, 10 to the 0 power is really just 1. So this is really just negative 1.083. Now here we're looking at a problem where it'll be a little bit easier to handle using numbers in scientific notation. So starting with the 1,920,000, I write that as 1.92 times 10 to the, and then this is a 7-digit number, so it's times 10 to the 6th. That's being multiplied by 1.5 times 10 to the negative, and it's got 3 zeros, so it's negative third power. That is over 3.2 times 10 to the negative, and that has 5 zeros, so negative 5, there's a decimal point there. And that's being multiplied by 4.5 times 10 to the, and this is a 5-digit number, so it's times 10 to the 4th. So the tougher part is going to be dealing with the digits here, the 1.92, the 3.2, the 1.5, and the 4.5. Really dealing with the tens should be quite easy, so I'm just going to look at that off to the side here. So like the 10 to the 6th and 10 to the negative 3rd, I add the 6 and negative 3 together, I get 10 to the 3rd on top. The negative 5 and the 4, I get 10 to the negative 1 on the bottom. Again, combining those, I really end up with a 10 to the 4th power. Again, you can think of moving the 10 to the negative 1 up or subtracting the negative 1 from 3. So the 10 to the 4th power is going to be the simple part. The part that will give me a little bit more trouble, and I'll probably just use a calculator for that, is multiplying these digits together. So in the numerator here, I get 2.88 when I multiply the 1.92 by 1.5. In the denominator, I get 14.4. And these are exact answers. I'm not rounding anything. So, and then when I divide, it's actually a 0.2. So I got 0.2 times 10 to the 4th power. And so, again, I could do this a number of different ways. 0.2 not technically in scientific notation, so but that would be 2 times 10 to the negative 1 times the 10 to the 4th. So that would equal 2 times 10 to the 3rd. And then I should be able to write that as a 4-digit number. That's the same as 2,000. Okay, so now here we're looking at healthcare expenditures. So $696 billion in 1990. By 2003, it had increased by a factor of 2.4. So write the 1990 healthcare expenditures in scientific notation. So 1990 healthcare expenditures, $696 billion. So let me just write that out originally. So $696 billion. So that's a 12-digit number, so in scientific notation it would be 6.96 times 10 to the 11th power. Now multiplying that by 2.4, let's multiply this by 2.4. So I'm really just multiplying the 6.96 by 2.4, I get 16.704. That'll be multiplied by 10 to the 11th power. Again, this would really be 1.6704 times 10 to the 1st, and then we'd still have the 10 to the 11th. So that would wind up being 1.6704 times 10 to the 12th. So really a 13-digit number. So there's my 13-digit number. So 1,670,400,000,000. So quite a big number. Thanks for watching.